Well, hello and welcome to the second of our videos on the part 4 of the chapter 8 material. Again, continuing to look at the addition across carbon-carbon double bonds. Continue, in this case, looking again where the partners in our elements in our X and Y molecule are of the same atom. So we talked about hydrogenation in the previous video where we had two hydrogen atoms. And now in this particular video, we're going to focus on the addition reactions where we have two halogens participating in that molecule. So a molecule of Br2 or Cl2 or even iodine or fluorine can participate in these kinds of reactions. And so again, we've got a carbon-carbon containing molecule here, and what we observe is as we add the elements of Br2 across that double bond, we get products that look like this, shown here already. Where if we look at them, what we observe is we get a pair of enantiomers. This results from what we call anti-addition. That is where both elements that are participating in adding across that double bond wind up on opposite faces of the product of the reaction. So the bromines are on opposite faces or anti, as opposed to, for example, we saw syn addition with hydrogenation. So anti on opposite sides. So we have to develop a mechanism that would explain this particular observation. So the mechanism that we develop for this particular reaction is that we think that, of course, that carbon-carbon double bond acts as a nucleophile in a way that we've discussed a couple of times already. And what we would expect as well is that attacking that bromine in the Br2 molecule with the double bond, electrons of the double bond, would result in kicking off that bromine-bromine bond with the two electrons going onto the bromine. But what we think happens as well, and of course we've got some evidence for this in this outcome of this particular reaction, is that the two electrons that are on that bromine also attack one of the carbons of that double bond to sort of satisfy the positive charge. And so we wind up with an intermediate that looks like this. So we wind up with what we call a bromonium ion. So a three-membered ring with a bromine with a full formal positive charge participating in it. And this intermediate is the one that's the most consistent with the observations of the stereochemistry that we get. So let's take a look at the fate of that bromonium ion on the next page here. So that bromonium ion, and of course the other partner that's participating in this is that Br minus, just kind of sitting around there with its negative charge, and all those electrons, maybe not too far away, counterbalancing that positive charge. But what we can imagine for that bromine are two possible pathways. And I'll draw one pathway here, for example, in red. We might imagine that coming on a backside attack in a way very reminiscent of what we saw for SN2 type reactions. So backside attack, kicking these two electrons up onto the bromine, satisfying the full formal positive charge in the bromine, and making that covalent bond satisfies the negative charge on that bromine. And so that red pathway can go over here and would lead to a product that looks like this. Where we've got now that bromine come in from the bottom face of the molecule, opening up that three-membered ring and leaving the other bromine sticking up above the ring. Now, how do we get to the other enantiomer of this molecule? Well, we can imagine another pathway here, which I'll draw in blue. I can take a pair of electrons and I can attack the other side of that three-membered ring, again opening up those electrons onto the bromine, satisfying the positive charge. The new covalent bond satisfies the negative charge on that Br minus. So if we look at the product of that blue pathway, again, we'd have one of the bromines pointing up above the plane of the ring, but that other Br minus that's following that blue pathway attacking the back side of that three-membered ring to ring open that. Again, very similar to what we saw with SN2. And then just to convince you that these molecules are the same, I'm just going to rotate that blue molecule 180 degrees. And if I rotate it 180 degrees, what you can see is that in fact they are enantiomers. Just rotating it on the plane of the paper 180 degrees so that the substituents line up and you see they're enantiomers with respect to each other. And so that enantiomer, the formation of the enantiomers is evidence of this bromonium ion intermediate and the fact that we get that. And so what I want to take a quick look at next here is the stereochemistry of the addition to acyclic alkenes. So in order to take a look at that, well, let's look at a couple of isomers of a related alkene here. So we'll look at two isomers, the E and Z isomer of this alkene, and imagine what would be the outcome of addition of Br2 in this mechanism. What would we get as products? So in particular, what would we get for the stereochemistry of these products, keeping in mind that mechanism with the formation of the bromonium ion, which then in turn gets opened by that nucleophilic Br minus that's added there. So let's focus on the E isomer that we would get with this reaction with Br2. We get two possible products out of this particular reaction. We'd get one product where it's added across that double bond where we wind up with one Br going backwards, away from us, another bromine coming this way, an attack, and that bromine going that way. Now the other product that we would get from this E isomer here would look like this. So these are both what we would describe as the anti-addition here. The anti-products, I should say, where the bromides are on opposite side of the molecule that we draw it in this fashion here. But these are enantiomers of each other. So if you draw them out or make the model and line them up, you'll see they're enantiomers of each other. These are the only products here. Those are the only products that we get. Now, let's compare it to what we get with the Z isomer here. Similar kind of analysis with the Z isomer. Again, with bromine, Br2. We can draw two possible products here where we form that intermediate bromonium ion and then ring open it with that nucleophilic bromine. And so what I'll do here is I'll draw them here. Just to show what we would expect to observe just from the addition across that double bond, keeping the substituents in place. The other thing we would get here would look like this. That bromine goes back. We would get those. We would get those as products. But now, of course, if we're looking at those, we recognize those are not the lowest energy conformations. So I'll put those on a fresh screen here. And what we get if we redraw these in the lowest energy conformations where these, again, we would refer to as the syn products, where both participants that come in, both elements of bromine that come in are on the same side of the molecule. Now, it's still the same mechanism. We get formation of a bromonium ion and ring opening, but then subsequently rotation to the lowest energy winds up putting both of those on the same side. So maybe if we look at all of these reactions together on these two different isomers, we can kind of summarize what these results show us. So here, if we start with the E isomer, we only get what we call the anti-product. We get a very specific product based on the stereochemistry of the outcome. And the other isomer that we start with, the Zed isomer, leads also then again to a very specific stereochemical outcome. In fact, the two products are diastereoisomers with respect to each other, the syn versus anti-products. So this addition across a double bond is another example of what we call stereospecific. Where the stereochemistry, in this case the EZ isomer that we start with, leads to a very specific stereochemical outcome, either the anti or the syn product, based on the configuration of the starting material. So we'll leave it at this for now. In the next video, we'll take a look at another kind of addition across that double bond.